Hi guys, first I wanted to welcome you in this YouTube channel. This is the very first video of the series and I hope this is not the last. And also, I hope you like it, of course. So to celebrate this, I wanted to talk to you about something I called the roll D.O.R attack. So, how to get permanent access in GarageDAW. So we'll see how we will actually abuse of a feature in order to get our permanent access. And to do so, first we'll introduce the rolling code, the remote using the rolling code. So as you may guess, we'll not talk about fixed code remote, but only rolling code remotes. And we'll see how in radio we can actually do some captures, decode the button press, the key press, how we can then generate key presses with the rolling code. Then we'll see together what is the D.O.R feature that I wanted to talk to you about, and then how we can actually mix the D.O.R feature with some attacks in order to get permanent access. So to begin, let's see some targets in here. So in here you can see the receiver, which is in here. You can also see some remotes. So actually, there's like the one remote here, and another remote that I will actually use in the real GarageDAW thereafter. But yeah, first I wanted to do something very comfortable in here because I don't wanted you also to see the wall attacks and also to make the video in front of my GarageDAW because it's not comfortable. So I just remade the environment that you see in here. We have the receiver, we have the remote. The remote actually, when you press a button that is not known, you will not have anything in here. But if the button is memorized in the receiver, and also the receiver knows the remote, you will normally hear like a little click, like. So yeah, and also we'll see about the D.O.R because the D.O.R we also, you will probably also hear like a very loud sound using the D.O.R feature, but we'll see that a bit later. So now let's create our project in GNU Radio, and to do that, we need, for example, we'll just like define a new ID in here. We'll use, whatever, could be like RxUSP remote, like that. We apply the changes. We use a sample rate which will be like convenient for us to get all the samples without problems. So yeah, by default, a lot of people use 1 MHz, which is like enough generally for this kind of remote. If you want to generally also maybe identify which frequency that is used by the remote, we can always like increase this value. For example, you can increase it to 40 MHz like that, and like that you can you can have like a better bandwidth to identify in which frequency the signal is shown. But let's use like 1 MHz. So we'll also make use of a QT range for the purpose. So let's create like now a variable like that, frequency frec. We'll not use any value for frequency. We'll use a QT range. So yeah, for the QT range, we have to know that, for example, in here, our remote uses a frequency which is like a 433.92 MHz. But we will not take into account what is written on the remote. We'll just like take into account what we see on the PCB, which is generally the case that we'll see. So you can see that the PCB generally indicates that the remotes use like an ISM band like the 433 MHz, but also the 868 MHz. So now let's use GNU Radio in order to see that. We just like first use like the frequency label in here. In here we just like do like frec range like that. Default value 33 MHz, 32 as a beginning. We stop at this value. We step at 100 kHz like that. It's perfect. So now QT range like that. Okay. All right. So now let's use like USP source. So we just like precise to the USP source what is the frequency that we'll use. So I'm just like indicating frec, like that would be okay. We use like a QT sync like that. to see what is happening over here. And we just like precise also the freq variable. We'll also show the freq. So then we just like create our project in here. First project rx USP remote, like that, and then let's see what happens. So we can clearly see that, for example, we have some sort of some noise, could be like thermal noise also. But when we try to actually send some signal, for example, with the remote, so we try to, for example, to send the signal like that, we can clearly see that, for example, in here, our signal is not going up. So we probably have to also, I forgot to disable something for this USP, is that because I have also plugged the USP on the TRX antenna, so I have also to configure it in here. So we go to the RF option, we change the TXRX, we apply the change, and then should be okay. Now let's try just like pushing some button, what's happening, and generally I will not see anything. So I will just like keep a max all in here until I see something, but let's just try to slice to some frequency. I can see that there is like something happening here when I push the button. So maybe if I just like go up, I will see in here, I can see some images. So that it doesn't mean that the signal is in this frequency. It's just like, some sort of image. So I have to increase the frequency like that. And so I will just like use a max hold in order to get exactly that. And so I can clearly see that the frequency which is in use is 432.92 megahertz. So like that, I can directly specify on the default frequency that we are using that, and I can also record the signal in order to, to avoid me to push the same button all over again. So let's try to just like use like a file sync in here. We'll record the signal like that, and we will record it as TMP remote button A. File like that. Okay, so now let's just like restart that, and then we try to capture what is going on so we can clearly see what is going here. I'll just like probably make a better capture like that. Okay, maybe a better one because my signal is a little bit low, but I can also manage. Yeah, I will manage with that. It's not a problem. So now I just like push one button one time. So I will just like use exactly the same samples all over again. So I will just like disable that for the moment. So I'm just like trying that, and then I will just like use a file source in order to see what happens. But first I need also to use a throttle. Because now I'm just like doing some simulation with the file, and if I don't want to overconsume my CPU, that could be great. So yeah, let's see what is going on in here. Yeah, I forgot also to use like the TMP. Where's the file? Remote button A, so I can directly apply the change, and I can see what is happening. So yeah, I can clearly see what is happening. I can see also the waterfall. In the waterfall, I can clearly see that I'm facing something that it is like a 2FSK or binary FSK, or a so-called FSK without precision. But yeah, a lot of people say FSK by default, calling the 2FSK actually. So yeah, we clearly see like a space and a mark that indicates a 0 and 1. So let's try to filter this signal in order to decode it. So yeah, also we have to take into account some parameters in here by looking at the waterfall. Is that, for example, in here we have like if we do like the difference of these two bands, we should normally see that there is like a 20 kilohertz difference. So yeah, clearly you can also see in the max out, for example, with the FFT. So yeah, we have like this frequency and this frequency like that. So yeah, we have like a 20 kilohertz bandwidth. So we just like filter like 25 kilohertz around with a low pass filter. So let's use like a low pass filter in complex. So let's now use the variable in here. Variable, let's call it like, for example, I don't know, cutoff. It is the right term. So a cutoff of 25 kilohertz. So yeah, if you are used to use, for example, real representation, generally a low pass filter is not relevant because you're thinking about using a baseband filter. But in here, because we use complex, we generally use a low pass filter that reproduces exactly the same thing for this representation. In here, because now our signal is well centered to 0 right now. So in here, we'll not touch anything on the decimation, etc. We'll keep exactly the same sample rate. We'll just like use the cutoff that is precise in here, and we just like use also a transition wave, which would be like, I mean, by default like that, a tenth of the cutoff like that, and then we see what happens, and see if we see what happens, we can clearly see that all the noise that was around is, filtered, and we have only the essential, right? So now let's see, because we face a FSK signal, we need to demodulate it. So there's like two ways to demodulate that. We can demodulate that with the FM demod, which is like quite simpler than using like the quadrature demod. But the quadrature demod is also quite, helpful because you have very few parameters. So I prefer generally the quadrature demod to do that. So let's just like see that in here, I will just like, I can also, put the Qt GUI sync in here. If I want, I just want, for example, to use directly the quadrature demod, and then I want to use the Qt time sync to see, the changes. So I will use an input float, input, control panel, trigger, auto, apply, and then, I forgot that I have also to import mavp, because I use like mavp in here. I have also the deviation. Oh, I forgot about the deviation. Let's see. The deviation. If I recall correctly, the deviation was because the bandwidth between the mark and the space is 20 kilohertz. The deviation, the maximum deviation is 20 kilohertz. So now let's just like import mav from here, like that, and then we have also the variable that I must create, which is which I will call FSK deviation, like that, and then I can copy the ID in this variable and use 20 kilohertz deviation, right? So now that I have done that, I can see what is happening, and I can clearly see that I can see some, some level of 1 and 0, but also some junk. So if I want to get rid of that junk, I can use a skelch, because actually Sketch is good for that. You can trigger for a specific dB and get rid of the rest. So we can just like use, for example, Sketch or simple Sketch, which is like has very few arguments. Parameters. So I can probably use the Sketch just after the low pass filter. So like that, it will be better. Like that. Okay, for the threshold, I will just like bypass that. So for the threshold, I probably also see in here what is the threshold that I have to use. So like let's use like minus 62 dB, alpha 1, and then I just enable this block, and then let's see what is going on. So now clearly we just got rid of the junk that was before, and then we can continue. So after the demodulation, we need something that is very important. We need at some point, because as you may know, the signal is, if you remember, the signal is always like sending a lot of a lot of repeated symbols over the time in order for the receiver to synchronize with this signal. So we need also to to remove the same, all the samples that represent the sample 1 and get only the initial bits. So to do that, we can clearly use, for example, there was like something called like a clock recovery which is deprecated in this version of GNU Radio, in the new version of GNU Radio. but you can always like use another thing that is called a synchronization clock, which is like an upgrade of the last recovery mode. So now let's just like change the type in here. We just like use quadrilateral mode like that. We can always like use like the Qt sync if we want. I mean, it is not a problem. Like that. We just need to do like another variable, which is like SPS. So let's create SPS like that. SPS 400. I mean, why it is 400? Let's see. I'm doing that by head, but if you just like record this wave signal, I mean, if you use like a wave file sync, for example, but I will also show you another tool for that. So test wave like that, and I will also just like encapsulate that. Okay, let's record that. I will also open Audacity in here. CT test wave. Let's see what is going on. So with a tool like Audacity, I can just like I can just like inspect the bits. So I can clearly also do that by hand if I want. But yeah, if I just like want exactly the number of samples, I can just like look in here. What are the number of samples in here? If I just like use samples in here, so I can clearly see that there is like close to 400 samples to represent a one. I mean a bit of one. So now I can just like go back to the project, and as I have just like guessed that it is only 400 SPS, I can use 400 SPS. I can just like let also the time error detector as Muller remainder, which is like the most common one, and also other parameters I can leave all the parameters as they are. I mean, I can just like readjust them if I need, for example, if I find any issue on the synchronization. So now let's just like re-enable that. I will use probably also maybe a virtual sync in order to make this flow graph a little bit nicer, because now it's becoming a little bit complicated. So let's use like a file source in here and a file sync like that. The file sync, I will call it after sync like that, and then I can just like use the virtual source like that after sync. I can use the Qt time sync like that, and I can inspect what is going on right now. So let's see what is going on. So I can clearly see that, for example, my synchronization block could retrieve, I mean, the 1 and 0 properly by just like leaving all the repetitions, but there's a problem with the level of the signal. So maybe I can adjust that using a AGC at the beginning of the clock, the simple clock. So let's try that. I will use also a reference gain of 0 for now, and let's see, now it's a little bit better. So yeah, I can clearly see what is going on. I mean, my signal has a nice level right now. I can also use then a throttle, I mean a threshold, but like that I can just like inspect what is going on. So I see, for example, that I have my bits that are here, like 101, 101, etc. So yeah, it's quite cool. So yeah, but I see another problem in here, because I can clearly see that, for example, at this step, my signal, I have a spike drop in here. So maybe I should do something about that. I mean, depends, but yeah, if I can decode at least one frame properly, it's not a problem. But yeah, I can clearly see that, for example, in here, there will be like some problems by decoding the signal properly. So I will just like use a threshold in order to clean a little bit this signal. So let's use a threshold that's use like okay, 0, 2. We'll use like 0.2 and okay, minus 0.2 levels. So like that, our signal will be a little bit cleaner. So let's use like the threshold like this. Then minus 2, Okay, and then yeah, let's see. We just like use 2 input in here. I will also give some names. So after sync, after result, so I can also debug what is going on. It's very cool always to debug what is going on like that, to inspect, and then I can clearly see that, for example, my result did a really nice job by just like leveraging, for example, this signal to a byte 1, etc. So yeah, actually, or 1 1 in this case, because in here the smaller period indicates a 1, there's a 0, then there's like probably a 1 1 just after. So yeah, that's cool. We can continue. So now let's maybe just like, because we'll not do that by hand, we'll output it in a file. So we'll just like use, for example, we can use like a binary slicer, but if we use a binary slicer, we have to just like, put it in the right level between 1 and -1. So I will just like use a float to chart. So let's use like a float to U chart after the results like that. And then I will also, because in here I will produce a file, but yeah, if we just like put everything on the file, in the file sync like that, we'll just like have like some bytes that represent a 0, 1, 1, etc. So we have to repack also the bits. So we have to repack everything like that. We repack bits. We use MSB. So we just like get one bit. It will just like assemble all the bits to form 8 bits in order to output just 1 byte out of that. So it's just repacking stuff, right? So then we can output everything on the same format. Now we call it binary file. And now let's pray. We probably also not repeat the samples. So like that, we can be sure that, everything is finished. Okay, so now should be finished like that. So let's go back in here and use, for example, our best tool, which is like xdump binary file, and we can clearly see that, for example, we could decode something interesting. There's like some level of 555 and also AAA normally that should be like interesting because it represents actually your duty cycle that you have saw at the beginning. I also like that. But yeah, if we just inspect the signal a bit further, we can clearly see that, for example, there is like maybe much more than 2 bytes of AA. There's like 3 bytes generally, and that could be like an interesting signal to work on. Maybe there would be like some errors, but we can always adjust all the errors by just like, using, for example, tricking a little bit with the simple sketch, JSGC, or the Trezor. Sometimes just by managing like that, we can retry everything we want. But there's also another method. So you can also use, for example, other tools, because if you're lazy like me, you will probably use, like, for example, a tool called inspectrum, and you can, for example, try to decode what is going on, make sure that it's on 1 megahertz, and then you can just like inspect what is going on in here. You can clearly see like a signal. You can try to just like add some frequency plot in order to get the levels. You can apply a result, and then out of the result you can try to use a cursor to see what is the minimum amount of samples for a 1 or 0 symbol. So like that, just by doing that, we can see that we face, if we just do the math, we have like pretty much like 400 samples, because just multiply the sample period by the sample rate. So you have like a 400 samples per sample, like that. You can just like resynchronize everything like that, and so you can then export everything to std out, and on std out you should see something like that. So this is one way. Another way is to generally also use another tool called D.O.R. You can always like use D.O.R, remote button A, like that. You can clearly see that there's like a weak signal in here, but it was like perfectly decoded. It guessed perfectly like the samples per sample rate. which is like quite good, but we can always like also filter it a little, because the bandwidth that we have captured is a little bit too much. So we can always like apply a bandpass filter in here, exactly as we have done in the past in here, doing that. So yeah, also to do that, you can get rid of the first signal and focus on this one, which represent, as you guess, the first AA that we have recovered early. So now, as we can actually, what is cool with this tool is that actually it has all the tools in order to inspect your signal. So for example, this is probably the command that is interesting for you. So let's maybe just like copy it to a nouveau signal. So let's call it like button A, like that, and then use button A like that. So yeah, it's probably not encoded in RZ because generally when you see something like that, some duty cycle, etc., and some other bits, sometimes you may be looking at some Manchester decoding, but just looking at the bits in here, it seems like there's like only like two values, like 100, 110, 1100. So that means that there's like some sort of encoding that is called PWM. So I have already done like some PWM decoders, but I can also show you that this is like pretty simple with URH, just to sell you URH. So as it is PWM, values can be represented like that. So it can be like 110 to be a 0, or 100 to be a 1, sometimes the inverse. So let's see, just like using, for example, this first assumption, like 110 represent that, and 11 represent that. So like that, maybe we could decode that a bit better. Sorry for that, I just also forgot to save that. So substitution 110 0 11 like that 1, and so I would just like save it as a PWM new 2. So like that, you can directly use that in here, and you can also see the difference. So you can see that, for example, you have something like that. Sometimes you will probably have to also to get rid of the duty cycles, because it was applied only on some bits. So for example, I can, for example, just try to get rid of that. Just take only these bytes that represent some PWM signal. That would be probably proper than that. And I can just like new button 1, I'll call it like that, and like that, and normally I should have like also an X representation which looks as follows. So I can probably also like that, I can see what is after the preamble and after some sort of synchronization bytes, but it's probably something else. Maybe it's part of these bytes, but for the moment we should probably inspect the wall, the wall bits in here. We can always like try to use the roll NRZ, because the roll NRZ can be directly used to, you don't need to encode it to send it over the air like that. You can directly send it over the air. So if you want to send it over the air, there's like a generator you can use like that, and you can change the bits as you want, but you cannot directly change several bits or several eggs in a simple time. So after that, I will show you how you can generate your own signal using GNU Radio. So yeah, we have a beginning. We know we have like one command for now. So maybe let's see what is going on with another command. So what I wanted to show you is the markdiff protocol, which is quite also convenient. That can be used then in order to recognize all the bytes. So we can probably also see, what we can do is that we can just like record over signal. Wait a second, in here I will just like re-enable button A, button B. Okay, I probably just like copy that and make another project like that. Sample rate 1 mega, like that. Okay, so here I'll just like specify directly the frequency, because I'm lazy, and gain value, and that would be that. Okay, yeah, I could also, I mean, yeah, that's the problem. I could also also sniff, I mean, use another gain, because the gain, this is also why also the signal is pretty low. I can also use another gain which is like maybe better for the reception, but yeah, still I have to be like very cautious about that. So it's nice to raise the gain. If you see that the signal is pretty weak, you can always like raise a little bit the gain by 10, by 20, but don't raise the gain like, you know, at 100, because you will probably break your receptor as well. So but I will just like do RF option, I don't know, I will just like re-enable that, button B, like that, RX only, RX only, RX only, like that, remote RX only, like that. And let's see with another button, push. So I'm just pushing another button. So I'm just like doing that. So I will push like this button actually in here. So let's see what is going on. I will probably also put a sync in here to see what happens, because for the moment I'm doing that in blind. So let's see. All right. Okay. Can see a signal in here. Super. I probably just like do one push, because I will have a lot of other values. Okay. So this is the push of the button B. So now let's go back to URH directly and do the comparison. So we can import, for example, we can go back to button B. We can just then select what we want in here. So this is this content, like that. So I will just like create a new button B. And so I will probably just remote button B. I can compare all the values that are in here. So I can actually see that there's like some changes in here, but still, I mean, yeah, there's like very few change, but still the encoding counts a lot. So generally, this is also why it's better to generally use this encoding, so you can clearly see what is going on here. So yeah, we can see that there are some change right now. So some change are probably due to, yeah, probably not. So there's probably like the command that is in here, and here there's like probably some, you know, I mean, some rolling code values. I mean, some values that will be encrypted and also a little bit random for now. So yeah, if we try, for example, to just like record the same button B all over and over, we can, for example, do that like that. We can just like try to record another command. Like that. I have done like 2 commands in order to see what is going on. So let's go to the interpretation. I will just like go to open, reopen a button B like that, and then look at the representation in eggs. Take that part. So the new push 1 like that, and the other is in here. So I will just like select that. All right, new button B, push 2, and so go to the analysis part and then see exactly what is going on. So I'll just like, delete that for the moment and see the differences that we can see. So yeah, in the NRZ you can clearly see that, for example, the commands that we have interpreted just before, if we just like look with the button A, sorry, new button A, wow, like that. So yeah, oh, like that. Yeah, better. So now seems like there's like something missing in here. Button 1, 2. Okay. So now you can clearly see that, for example, the button B can be, I mean, the command can be clearly seen here. If we just like decode everything in D.O.R.Jam, you can clearly see that the change appears in here. So this is probably maybe the command part. So let's maybe call it like the command part. Command in here. So now in here you have probably the preamble. Preamble, and then there's like in here it seems like here there's like some fixed part. So I don't know if this part yet is I mean, in here there's like also some padding, so I can just like pad it a little bit. But here it appears that there's like some fixed part in here for the moment, so we can call it like fixed part. So yeah. And here there's like probably like the rolling part, I mean the encrypted part. Encrypted data. Data. So like that you can clearly see that, for example, you can just like reverse engineer your key, and you can actually see that, for example, on each push the button, I mean the value will be different. So that means that we are actually facing, I mean, a rolling code. So what is rolling code actually? So for microchip based remotes, you usually will encounter something called Keeloq, which is like an encryption algorithm that is used by microchip. Actually, it is implemented in a lot of HCS, or also some PIC 12, PIC 16, etc. So yeah, as long as if you deal with a microchip based remote, you probably see like a Keeloq algorithm, not probably, but surely see the Keeloq in action. And also, I mean, if you're not sure about which type of chip you have, you can always like dismount, I mean, your remote, and see that, for example, for the microcontroller, this is like a small M that generally, I mean, looks like the logo of a microchip in here. So yeah, I mean, you just need to do that. So yeah, so how it looks like. Actually, Keeloq, I mean, there's like some other version. I mean, there's like no just one version of the Keeloq. It could be like several that fix some vulnerability as well. And you can have also two types. You can have like a hopping codes, generally for our target is the case. Hopping code, I mean, in each press, as you saw, there will be like another code that will be generated all over the time. So yeah, this is how it looks like, is that, for example, for each key press, there will be like a synchronization counter that will be used, that will be different for each key press. So I mean, finally, your encrypted part will be also different each time. And also, you have also the representation of the clear text data. So as we saw before, for example, with URH, you can correct a little bit all those bits in order to make some sense in it. Because, yeah, as I saw just before, I mean, without any documentation, I was like trying to blindly reverse engineer the communication. But yeah, once you have the documentation, you can always try to match a little bit more the data that are sent over the air. So yeah, so I was talking about the hopping code, but there is also another type of Keeloq that is not. I will not talk about. It is the IFF. It is the Identify Friend of Foe, which just is like a challenge response. So actually, this is like exactly the same way as, for example, you remote key for the car, for example. So the car will generally try to wake up your tag, for example, and you will just like respond to a challenge from the car in order to identify yourself to the car in order to, for example, open it or start it. But this is not the case for our case, for our context, so we just like keep on the hopping code. There are some known attacks on Keeloq, so just for your information, I'm just like giving you some references. So yeah, actually the dumbest attack you can actually do is the RollJam attack. So you have probably learned or heard about the RollJam attack, but yeah, as you may know, there's like no nonce, no timestamp. So actually, you can, for example, if someone is in a nearby, and you sniff the key press of someone far from the target, you can actually open the door by just replaying the same signal. Or you can also do some jamming attacks, so you can just jam, for example, the receiver side in order to block, for example, the receiver from getting the signal, the button press from the user. You can keep, for example, 2 key press, and then you just like after you have like the 2 key press, you can send the first key press, so the guy will probably just like maybe close the door, open the door, and then you keep the second key press for you to reopen the door, for example, if you want. So yeah, RollJam attack is just like a jamming attack mixed with a replay attack. Yeah, there are also some encrypt analysis that have been made. So there was like some sliding techniques, plus linear approximation by Andrei Bogdanov, sliding algebraic method, etc. by Nicola Courtois et al. And also over the time when Microchip also fixed some vulnerability, there was also other attacks in order to leverage, for example, the brute forcing. For example, because at some points as we have solved just before, we need to, in here, we need the crypto key, which is unknown, for example, so we need to get out the crypto key, and we need also the synchronization counter. So if we have one of the unknown parameter, we can always like try to brute force the other parameter. So this is the purpose of every rolling code attack. And in here, there was also some there was also some such channel attacks to extract the key, but there's also some ways to extract the key just by dumping the firmware, for example, if there's like no reading protection mechanism, for example. So the first attack that you probably know is the RollJam attack, because in here you jam, you listen for 2 commands, and then you replay the first commands just to fool, for example, the user that, for example, the command worked, and then you replay the second command in order to open the door. But there is something that can be interesting for our purpose, because in here we have like, for example, for some systems, there is like a feature which is called D.O.R. Actually, I don't know what D.O.R means. I try to search everywhere. Maybe I'm not very good at searching at Google, but yeah, that's the fact. But yeah, I didn't find anything about what is D.O.R. But D.O.R stands for. But D.O.R actually, it is just like a procedure that helps, for example, users to add new remotes remotely without having to manually touch the receptor. So it is a cool feature for us, because as an attacker, if we are able, for example, to get the key, the synchronization counter out of after that, we could be able, for example, to generate, for example, maybe a D.O.R command that will allow us, for example, to introduce new remotes for that. But I will explain that a bit later. So yeah, some cloners actually use exactly these commands, like the YFO. So if you are interested about how to copy, for example, your remote, you can always like use this kind of remote that actually implements, and this is pretty funny, because they implement actually the attack that I will show you is that you just like, for example, get 1 key press from any receptor, any transmitter. You then try to increment the synchronization counter, and then after incrementing the synchronization counter, you can create, for example, an ROD signal. Then you produce another signal, which would be the key press of the remote, and then you can add a new command into the system. So we'll see that in practice, because maybe it's a little bit confusing. So let's see that together. So we just like see how it works in here. So yeah, the UCP will not be used in here for the moment. We have to know that, for example, there's like, for example, for this command, I mean for this remote, there's like four buttons in here. But there's a button that we don't see, and the button that we don't see in this one actually. This is actually the feature that I was like talking about. This is the RollJam feature. So yeah, if you want, for example, to make use of this feature, what you have to do is to actually push this button, and then something will happen, right? So let's do that. I mean, we'll just like let's use, for example, that. I will just like push this hidden button right now, like that, and as you can see, there was like a small sound like that. So there's like exactly two sounds. There's like one sound that says, okay, let's create a new remote, and the other one is the end. But if you have like in the beginning, if you have like a long signal, that means that, for example, someone pressed use like the remote, for example, that I have here with a synchronization word that is like newer than the one that is used, for example, for the RollJam feature. So what we're gonna do now is just to sniff this command, because it's kind of interesting, right? So let's see, for example, in here, we just like go back to D.O.R, to GNU Radio. And so let's see, with GNU Radio, we have like, we just like do that a little. So I will just like capture I will do like a new capture in here. So I will just like push the hidden button, which is like the D.O.R button. So let's start this flow graph. I'll probably just like remote, that will be like RollJam, like that. And then let's see. So we have a signal that is on the same frequency, which is cool. So as we have like recorded this signal, we can make use of D.O.R right now, and we can decode it. So let's go to remote RollJam, like that. We will just like do some filtering. Like that. I will just like skip that. And then I will get the eggs representation, get this command like that, create a signal out of it, and then eggs. I will call it differently, like hidden button. All right, let's go to the analysis, like that. And on the analysis part, we can see, we have also to change the encoding. Okay, we can see that now we have a different command. So in here, that was like the button A. This is the button B, and here is the button, the hidden button, right? And it has in here, the bytes also we see in here increase. So maybe that part is also part of the command. So yeah, we have probably just like, we need to just fix that a little. So preamble and fixed so like that, confirm. And so yeah, I will just also edit that. So it starts at 24, and so like that I can just like precise that now this part is probably just like the command. So now also you see that the fixed part, I've just shown you the just one command, but if I take another command, this fixed part will change also. But the rolling code change a lot. So what is interesting also with the RollJam feature is that the command is still the same. If you push, for example, this button, you can push it. I mean, you can replay this command all over again, every time you want, because actually it does only check if, for example, the synchronization counter that is used by the ROD feature is greater than the last button push. So this is pretty interesting because, for example, if I'm trying to replay exactly this signal, you will hear exactly the same sound that is like the same, very quick sound. Then after some time, there will be like an ending sound. So let's see that. Let's try to replay the signal. So we just like try to, we'll do like another project in here, and we'll just like call it like TX user P, TX user P, like that. Sample rate, we'll use exactly the same sample rates as for the capture, and then you will use the file sync. So the file source, the user P, like that. Sync. We'll just like make use of the same frequency, 433, like that. Gain, let's use like, for example, the 20 gain, like that. As before. File, let's use overlocation, TMP, ROD. All right, apply. We'll just like repeat one time to see exactly how it sounds. So overlocation, yeah, whatever. So now let's play it. Oh, so probably I try to save it in the wrong place. TMP, whatever, like that. And doesn't do anything. Let's try to see why. ROD complex, RODC file. Remote ROD. I will also maybe use a sync to see if something happened. Right, I just go back to the same signal. Source, remote, all right. I will just make sure also that oh shit, yeah. I'm a little bit tired, sorry for that. The frequency was not good, so now it will be better. So as you can see, this is not fake. So let's see. It does the job. Oh shit. And now, yeah. Now it will be better. If you want to work, RF option, TX, RX, gain, on the right frequency. Just like making sure that I'm on the right frequency. dB, sample rate, it's good. Absolute, only that. Okay, gain value. Normally should work. So let's see now with doing with the USAP, trying to launch everything with the USAP like that with the right parameters, if it works. So we just like launch everything. Let's try to replay the same RD signal, and you will see it's working, right? And now we can replay exactly the same command all over again. I mean, there's no synchronization word, checking in this command. So this is good because actually if you just like take one of this command, if you're able to take, the last key press of the command, you can actually, register another command. So yeah, particularly how it works is that, for example, if I'm just like trying to, if I'm just like with the remote, I'm trying to I would just like resend the same capture. And what I will do is that I will register a new command, new remote, which is this one, which does not do anything in here. It's not registered to this receiver. So what will happen is that now we'll use the signal, the ROD signal from this receiver. I will use this command in order to register the button A as the button A that should be used for or the button B, but the button A actually that will be, that will be the button that will match the button that I will press. So if I want to register the new button and the new remote with this button or the button B, then I will have to push the button B after the ROD signal and after the key press of the button A in here. So this is how the remote, the remote programming works actually. So let's do that. I will do that like that. Like that. And normally you have a long signal. That means that everything was registered properly, and so this command that was not registered before is able to, I can just like also, change the mic in here. So as you can see, I can just like open the door now. So yeah, as you could see, basically, you can replay all over again the same ROD feature button if you want, but at least you need also the push, the next push of the user that actually uses the button, the hide button. So at some points, you get nothing if you don't have like a valid button A or button B valid push from the user. You got the hidden key. So you can always like capture these two commands. For example, if you just like go to a bar, etc. So this is one of the attack, or you can also leverage, another attack, which is like the RollJam attack that you know, where as an attacker you just like take the command from the maintainer, you then jam at the frequency on the receiver side. You just like capture the pair remote button A on your side while jamming the receiver, and then you replay the ROD, the pair button A from, and then you key press from your side in order to add your remote on that. But yeah, it assumes that there is like a maintainer that will just go into, add another command. So you will probably wait, a lot doing that. So the first purpose, the first proposition was probably better just by capturing everything, on the bar or something like this. It is not as simple as just sniffing an HID, RFID card, but it is always a technique. But there is always, a but, and there's always another technique, and this is a technique that I will take to show you, because I want you also to show you another service that you can also use to generate your own commands, so generate your rolling codes. So the service in question is called Kaiju. It is like a rolling code analyzer generator, which is quite good. Normally, this service works with, a small device like I can show you in here. So I mean, with the Panda RF, so normally it should, I mean, it should combine, but I have like, I mean, I have some pains to try to make it work. I mean, to acquire the a proper FSK signal on the Panda RF. So maybe I have to work a little bit on the filters, or maybe on the distance. But yeah, we'll just like make use of the SDR. But normally, I mean, the Panda RF should be also able to acquire the FSK signal as well. But it is like a little bit painful. I mean, in my side, as I'm just like very used to use SDR and to analyze stuff and to filter by my own, I mean, to do everything from scratch sometimes. I mean, using a tool that does everything on you, I mean, automatically is like, I mean, complicated for me. Sorry for that. But yeah, maybe I will probably get it to work and also do another presentation about that. But let's see the series that actually works pretty well. What is cool is that, I mean, it includes a lot of supported devices. So you have like supported devices like that. You have several manufacturers. I mean, it's super cool when you see that on the paper. So let's see what we can do actually with that. And as well, you have the high-tech also PCF. So it's pretty great. What I will do is that I will maybe do another capture. I mean, I will make another capture. So let's just like make a capture of that. I mean, I will just capture another key press because I mean, I need also a fresh synchronization one, and I'm not sure about the one that I have provided. So I will just like make a capture in here, like that, push a button, then okay, and so then I will just like analyze it directly with D.O.R. I mean, like that I can copy directly all the bytes. So opens button A. Was it button A or something else? Wait a second. Remote. Oh yeah, shit. Sorry for that. I'll just like make another push. Button A, like that. All right. So now I have button A. I will get into Universal Radio Hacker and then push it in here, do the decoding. I mean, I will just like filter that a little like that. Take also the X representation, copy the X representation like that, and then I will go to Kaiju in order to analyze that. So let's go to Kaiju. I can directly copy the raw bytes of that. I can also generate some next 2 rolling code, but from now I just want to analyze it. So let's see also if the decoding was good. Yeah, it was, I mean, it was actually pretty fast. So it recognized also one of my remotes, which is like quite good. And also it could recognize, I mean, the model, etc., the serial number. I mean, there's like pretty everything. I mean, you have also the cipher that is in use because obviously it is microchip, D.O.Rjam as an encoder. And if you want to generate some other running code, I mean, this is pretty simple. You can do like, you can also select which button you want, which could be like important in further, just after. You can see that the starting counter is this one, so I will just like use a starting counter like this one, just to increment it a little. I will generate one running code only, so let's generate it, and then you see your packet was what was generated. So let's go back to D.O.R, but the thing is that, for example, with D.O.R, you can actually try to, I mean, you can always like, sorry about that, I will just like clear the table and like that. So you can always like try to, I have like the X representation. You can always like try to, I mean, to modify each column, etc. I mean, I didn't saw any option in here for the moment that allows you, for example, to directly import an X. But I mean, because we are a little bit lazy of doing that. I mean, step by step. What we'll do is that we'll actually create our own modulation. So to generate our RFSK signal, what we'll do is that we'll create a new project in GNU Radio. We'll call it like, TX remote, whatever. We use a sample rate, which will be like the same exactly as before to match the bitstream, and then we do the file source that will acquire some bytes out of it. So let's use like TMP new rolling like that. Will not repeat it. Then we just like change the type. We have to also unpack the bits from the bytes. Remember, so we'll do that like that. All right, unpack 8 bits like that, and then we will just do like some repetition in order to, if you remember, we need also to, to repeat all the samples 1 and 0 in order to, to synchronize with the receiver properly. So let's do that. We just like do 4 like that, and then we have to align a little bit. We'll just like make use of U chart to float in order to change it to float, because then we'll use like a frequency modulator that use only floats, and then we have to recenter the signal to 0 and also to preserve the bandwidth from the maximum deviation. So we need also to compute a little bit all the samples in order to preserve this market space bandwidth. So let's just like multiply our signal by 2 like that, and then we subtract by 1, so like that we'll have a signal which will be compressed between -1 and 1, and like that it will be recentered to 0. So like that. Then we use the VCO. There's like a VCO, you can use a VCO, or you can use also the frequency modulator. Doesn't matter. It does exactly the same job. So we use like VCO like that, sample rates, is only that. The sensitivity, it's 2 pi, and then you have to precise also the deviation in here, divided by 2, because if you don't divide it by 2, you just double the bandwidth. So yeah, this is not what you want to do. And then you can define, for example, an amplitude. So you can define this amplitude, for example, at the beginning, but you can always like use another amplitude after. So now let's just like also I forgot I have to also import matpy. So from mat import pi like that, and then no errors, right? So then let's see with a Qt GUI sync what is going on. So I can just like be sure that everything is worked. Project remote like that. TX remote like that. I cannot open the file. Oh, sorry. I forgot also to put what was in Kaiju. So maybe let's just like in TMP it was like new rolling. Okay, so let's just like in Python 3 what we'll do is that first we'll just like take this string like that. We'll then convert it, so it will be like bytes from eggs, yes, like that. So we have something like that, and then we open a file, temp new rolling like that, and then we just like write everything thereafter. So we write okay like that. Like that, perfect. So normally you should get something like that at the end, xdump new rolling like that. So it represents exactly the same code that was generated by Kaiju. And now let's see in GNU Radio what is going on. So we will just like look at the Qt sync, what is going on, and we see that it's completely screwed. So why exactly? Because I just forgot that it's not repeated, so it has already finished. So yeah, apply, okay. So let's see, okay. So now we clearly see that, for example, we have, and even in the waterfall, we have built like an FSK signal, which is 20 kilohertz bandwidth. So this is perfect. You can clearly see in here. So -10 and +10. So we have clearly our mark and space, which are well aligned, and everything works fine. So now that we have finished our modulation, we can actually send it over the air, right? So let's do that. But I will also, before that, I will also enable the mic just after in here. So wait a second. I will Qt and USRP source and sync. I will use exactly the same frequency as before. I use a gain like that, 3 point like that, and then just after that, just before that, I will enable just this mic in here, and let's see. What is interesting is that in here we are pushing a button A actually in here. You heard there was like a small tick that was sent, and once I'm just like keeping pressing the button, so I didn't it kept pressed for a while. So this is pretty interesting. So actually we are able now to generate our own button like that. So now let's see how we can maybe generate the hidden button signal. So if we just like go back to the Kaiju website, so let's see that. So yeah. Perfect, I'm here. So if I'm just like going back to the Kaiju website, I will just like show you that in here. Let's try to maybe decode the hidden button. So like that, we probably also be able to generate two buttons. And so if we are able to generate our hidden button plus the button A, we can actually add any remote we want as we want. It is like perfect. So if we just like try to analyze once again the code that was decoded just before, let me just like retrieve it in here, analysis. So it was like rolled button in here. I will maybe. Okay. So yeah, technically remote A. I'll just go back to the rolled button. Where is it? Okay, filtered. So this is this one. So yeah, if I try to decode it, let's see what happens. I will just like try to analyze it, and there is like something interesting, because now we don't have the button value status, which is 6. Which is 1 or 2 or 3 or 4. We have 6 actually. So this is pretty interesting, because like that we can actually we can actually do some bad stuff in here. So if we try to generate this button, number of button value, let's try 6 like that. Synchronization counter, we'll use like this value like that. Let's try to generate. But yeah, as you see here, it does not generate properly this button. And I don't know if, you know, this button was left, I mean, it is a bug, or it was left for some reason, and I can totally understand that it was made for some reason. I mean, it could be blacklisted for some reason, because if anyone is able to actually generate this rolled button, I mean, it would be like a mess. So yeah, as the service doesn't allow you to do that, there are also other ways. I mean, you can always like try to just like look at the chip and extract this secret from the chip. But I mean, this chip is like a little bit complicated because it's a little bit custom, as I tried to look at. And so what I came in is that I just like order another remote that is a little bit simpler, which is like the remote from Why-Ever, which actually implements the keys that are used by the remote. So you can actually, as an alternative, you can use this chip that is recognized that you can actually use as a reference. And so you can use the datasheet properly and dump what is in the memory of the microcontroller, dump the key and replay that.